Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Lecture 5, the chain rule. So last time we talked about the product and quotient rule, and this was what you would use as a rule to take derivatives when you multiply a couple of functions or you divide a couple of functions. The results from the product and quotient rule were kind of hit or miss. Sometimes it was easier to use the product rule, and sometimes it was easier to just, multiply these things out. The chain rule, I think, is something that really is beneficial and saves a lot of effort and time. And so we'll see an example of that in just a minute. But to kind of motivate what the chain rule is all about, I want you to kind of think about, what if we were to, for example, have, some number like 5 kilometers per second. Let's say that we had a speed written as 5 kilometers per second. We wanted to express that in different units, like maybe we wanted it in meters per second. How would we do that? Well, we would simply multiply 5 kilometers per second times 1 kilometer in the denominator, and we put 1,000 meters in the numerator. This is basically converting kilometers into meters. And what happens here is we end up getting an answer which is in meters per second. Now, how did that work out? Well, the kilometers here and the kilometers here canceled, and so we're left with units of meters in the numerator and seconds in the denominator. And I want you to think of that when you think of the chain rule, okay? Because that's how we're going to kind of link these things together. The way I would write it is something like this: dy dx is equal to dy du times du dx. The du's cancel. I'm left with dy over dx. You see that? This and this kind of cancel. I'm just left with dy in the numerator and dx in the denominator. And so that's essentially how it works. What is it used for technically? Well, you've got multiplication, you've got division. There's another operation that you might remember, composition, right? And so composition, f composed g, is equal to f of g, like this, right? If it's as a function, if both of these are a function of x, right, then this could be, as a function of x, and then this would be g of x inside of here, you see? The idea is that we substitute one function into the input of another function, and that is composition, okay? And the chain rule tells us what the derivative, I'll just write it out explicitly here, d over dx of f composed g, I'll just say as a function of x, is going to be f prime g of x times g prime of x. Now, how do we link that back to the Leibniz notation that we used before? Well, if I said that, y is equal to f of x, and then I let u be equal to g of x, then dy dx can be written as dy du times du dx. And that is kind of the link between this notation and the Leibniz notation. Yeah. Sometimes it helps to think of a physical example where this has some meaning. So for that, I'd say, and we'll do an example of this at the end of the lecture, but let's imagine a balloon, right, that you're blowing up. Okay, and let's say that the increase in the radius as a function of time is maybe linear, maybe it's quadratic, right? And that's the increase in the radius of the balloon. Yeah. R, we'll call it. So we have a function for r as a function of t. But we want to know, how does the volume of the balloon change as a function of time? So we want to know what dv dt is, right, where v is the volume of the balloon. So we can use the chain rule to derive an expression for the change in the volume of the balloon as a function of time, given that we have a function that tells us how the radius depends on time. And so we'll see an example like that in the end. But let's jump right into proving the chain rule. So let me first write down what it is, just to keep that for reference. So let's prove it, right? The proof. And the way that we're going to prove it is the way that we've proved the product and the quotient rule. We're going to use the limit definition. D over dx of f of g of x, by definition, by the limit definition anyways, is the limit as delta x approaches 0 of f of g of x plus delta x minus f of g of x divided by delta x. Okay, that's just our same old definition for the derivative in terms of a limit. Yes? You want to remember that? The only difference is that where you'd have x before, we have g of x plus delta x here and g of x here. You see?
Yeah.
So what I want to do next is I want to make a substitution. I want to let u be equal to g of x. And I want to call delta u g of x plus delta x minus g of x. And I want to introduce this terminology into this. So I'll rewrite this as follows. The limit as delta x approaches 0, f of g of x plus delta u minus f of g of x divided by delta x. So what did I do here? If you look at g of x plus delta u, well, g of x plus this, the g of x's disappear, and I'm left with g of x plus delta x, right? So that's all that's happened here. Yes? Do you see that? Just a simple substitution where g of x plus delta x has been replaced by delta u plus g of x. Okay? Make sense?
Yeah.
Now I want to multiply this times 1. But, you know, again, in math, when we multiply by 1, we have a lot of choices. In this case, I'm going to multiply by delta u divided by delta u. Okay? So with the caveat that delta u cannot be equal to 0, right?
Yeah.
Now I want to switch places here. Actually, I'm going to write another line. F of, not changing anything. It's just copying what I have written up here. But I'm going to switch the delta u and the delta x. I'm going to switch their places. That doesn't make any difference at all, right? Delta u times delta u over delta x. See? Just switch the places of these guys here, and that's fine under the associative property of multiplication. But now, let's look at what this is. What is this term? Or what is this term, right? Does anyone recognize what those terms might be equal to? So if I, actually I'm going to write it like this, times the limit as delta x approaches 0 of delta u over delta x. And if I were to substitute in for delta u here, that's g of x plus delta x. Let me just write it in. G of x plus delta x minus g of x. What is that? Anyone recognize what this is? This is just the definition of g prime of x, yes? What about this one? What is this? I do need to make one little change here, right? In this case, it's not the limit as delta x approaches 0. It's actually the limit as delta u approaches 0. And if I do that, then this becomes the definition of f prime of g of x. So what do we get? We get that d over dx of f of g, f composed g, if you want to say it that way, is equal to f prime g of x times g prime of x, which is, of course, what we sought out to prove. That is the chain rule. So you first take the derivative of f, treating it as if it's being taken with respect to g of x, right? So if f was like, you know, g of x squared, you'd say, what's equal to 2 times g of x, okay, using the power rule for derivatives. And then, finally, you do g prime of x, which is just the usual way of doing derivatives, right? So there's nothing unusual about that. If it's confusing to you at this point, I think, you know, seeing an example is really going to make it, you know, drive it home. It's not that hard. It's very intuitive once you start thinking about it. So let's do that now. Let's do an example. All right, so the first example I'm going to do is pretty simple. Let's let f of x be equal to, or if you want me to, I can write this out more formally. I can say f of x is equal to x squared, and g of x is equal to 2x minus 3. Okay, so when I do f composed g, this is going to be 2x minus 3 squared.
Yeah.
Because it's just take f of x and substitute in, instead of writing x, write 2x minus 3. So now we want to take the derivative of this. Now, before we do it, we know how to square things. We can just do this out. We can expand this out manually, yes? So let's do that real quick. Let's do the derivative of 2x minus 3 squared, which is just going to be the derivative of all of this. It's going to be 4x squared minus, I guess it'd be 12x plus 9. Yes? Looks right. I just squared 2x minus 3. Well, we can do this term by term. It's just the derivative of this minus the derivative of this plus the derivative of that. And that is equal to 8x minus 12. which I could rewrite as 4 times x minus 3 if we want. So we have that result. But now let's use the chain rule. So this is, just call it expand and differentiate. And then here we'll use the chain rule. D over dx of 2x minus 3 squared is equal to, well, first we treat 2x minus 3 as if it's like x, basically. So how do we differentiate x squared? Well, it's 2x. So if we differentiate it with respect to 2x minus 3, it's going to be 2 times 2x minus 3. If it was cubed, it would be 3 times 2x minus 3 to the squared, right? But now we have to do this part. We have to do g prime of x. We have to differentiate what's inside here. We have to differentiate 2x minus 3. What's the derivative of 2x minus 3? 2. So our answer is, well, 2 times 2 is 4, x minus 3, which is the same thing that we got when we expanded it out. Okay? So we see that it works. We've seen how it works and how you do it. So let me give you one to try. We're going to take the derivative of 2x cubed minus 5x all raised to the 5th power. And that one you probably don't want to expand out. You could, using the binomial theorem, as we've practiced before, but it would be tedious. So let's attack it with the chain rule. Go ahead and pause the video if you're at home, solve that now, and then resume when you're ready to see the solution. So what do we do? So we'll think of this 2x cubed minus 5. Just call it u in your mind if you want to. So really what you're going to do is you're going to differentiate u to the 5th, right? What is the derivative of u to the 5th? What's 5u to the 4th, right? Yes. So we write 5, but remember u is 2x cubed minus 5x, so we write 2x cubed minus 5x to the 4th power. Yes. But then we have to differentiate the inside. We have to differentiate 2x cubed minus 5x. So let's do that now. What is the derivative of 2x cubed minus 5x? Well, we do it term by term. And so we're going to multiply both of those terms times what we had at the beginning here, right? So 2x cubed, the derivative of that is going to be 6x squared. So 6x squared. And then the derivative of minus 5x is just going to be minus 5. And that is basically it. There's no reason to do anything else. I mean, if you wanted to try and multiply this in and refactor, you could, but I think it's going to be best to leave it as it is, right? There's no real benefit in doing that. So now we're basically done. You can see that was a lot less work than we would have done if we had to expand this out term by term and then differentiate it. Yeah. But we would have got the same answer. Let's take a look at a slightly more complicated example, right? This time we're going to look at it for, say, trig functions, because it's useful there. So consider f of x equals sine of 3x squared plus 1. And we want to take the derivative of that. Okay, I'm not going to write it out in terms of g of x and f of x again, so that we can show the composition, but you can see that this is like the function sine of x, where we've replaced x with 3x squared plus 1, yes? Yeah. And we want to take the derivative of that. So what is the derivative of this? F prime of x is going to be, what's the derivative of the sine? What's the derivative of the sine? Cosine. It's the cosine. So it's the cosine of what? Well, 3x squared plus 1. 3x squared plus 1 times, now we have to differentiate the argument inside the sine. So it's the derivative of 3x squared plus 1. Well, the derivative of 3x squared is 6x, and the derivative of 1 is 0, so there's no reason to add that term on. And so we get our final answer of 6x cosine 3x squared plus 1. Now let me give you one to try. F of x equals the cosine of 5x cubed minus x. So go ahead and pause the video, differentiate that now using the chain rule, and come back when you've got your solution. Pretty much the same as before, right? Except, of course, the derivative of the cosine is the what? What is the derivative of the cosine? Minus the sine. And it'll be of the same argument here, right? Of 5x cubed minus x. And then we differentiate the argument. So the derivative of 5x cubed is going to be 15x squared. And the derivative of minus x will be just minus 1. And so that is our answer. You could rearrange it any way you wanted to, but leaving it like that is fine. Make sense? Any questions about that? No. No? It is possible to use the chain rule on a nested composition. So what is a nested composition? That'd be, like F compose G compose H, compose I compose J compose K. This can go on as long as you want, right? Just think of it like this: dy so let's say dy dx is equal, now I'm going to write it like this. Dy dz is equal to dy dA times dA dB times dB dC times dot 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 all the way down to, oh, I probably shouldn't have used y here. Let me call it d alpha. Dy dz times, I guess that's good enough. Right? All of these things are going to cascade in. So we're left with d alpha over dz, which is what we wanted in the first place, right? Yeah. So we can cascade this as much as we want. Let's look at an example that will make it a little clearer. Let's consider f of x is equal to the sine squared of 2x cubed plus 1. So now it's not just the sine of u, where u is 2x cubed plus 1. It's the sine of u squared, or it's u squared, right? Yeah. So does everyone see the composition here that's taking place? Maybe to write it out explicitly. So if I said f of x is equal to x squared, and g of x is equal to the sine of x, and h of x is equal to 2x cubed plus 1. Yes? Yeah. I do f, compose g, compose h, and you get this. Yeah. So we have three compositions taking place here. But that's not a problem, right? So how do we do it? Well, f prime of x, sine squared. What is the derivative of a square? U squared. What's the derivative of u squared? 2u. 2u. So first we write 2 times the sine of 2x cubed plus 1. That's the first derivative. Yeah. Okay? Now we have to differentiate the sine. Okay? What's the derivative of the sine? Cosine, right? Times the cosine of 2x cubed plus 1. Now we have to differentiate the argument inside the sine. The derivative of 2x cubed plus 1 is just 6x. So times 6x. And now we're done. We could simplify and make this 12x sine of 2x cubed plus 1 times cosine of 2x cubed plus 1 if we wanted. But it's fine as it is. Let me give you guys one to try. F of x is equal to the cosine of 4x squared plus 3 raised to the third power. So go ahead and pause the video, differentiate that, come back when you're done. You're already done. That's very fast work of you. All right, f prime of x. So we'll start with the cube. So what is the derivative of u cubed? It's 3u squared. So this will be 3 times, I'm just going to write it in parentheses, cosine of 4x squared plus 3 squared. Yeah. Times, now we have to differentiate the cosine. What's the derivative of the cosine? Minus the sine of 4x squared plus 3. And then we have to differentiate the argument. Times, the derivative of 4x squared is 8x. And the derivative of plus 3 is just 0, so we'll just put times 8x there at the end. You could collect the terms, move the minus sign over here and stuff like that if you wanted to. You could put the square in the other position we put for squares, right? Cosine squared. But it's fine how it is. That's the derivative. Let's look at some applications for this, okay? So we'll pull from a few different areas, physics, geometry, and economics maybe. Let's do an example in physics. So let's suppose we have a particle that's moving along a trajectory where its position depends upon the temperature, and the temperature depends upon the time. Maybe it's moving along some surface, right, where I'm adding heat to the surface, so the temperature of the surface is increasing over time. We'll let S as a function of big T, that's temperature, and S is position, be equal to, let's do 5t squared plus, what did I use here, 3. So that is its position, its dependence on position as a function of temperature. Now the temperature we're going to allow to depend on time, so little t. And we'll say that the temperature as a function of time is linear, 2t plus 1. So at t equals 0, it already has some temperature. So there's the dependence, and we want to know what is ds dt? This is, of course, the velocity, right? What is the velocity? So the position as a function of time. So how do we do it? Well, ds dt, right, is going to be ds d big T times d big T d little t, right? Rate of change of temperature with time, rate of change of position with respect to temperature. Make sense? You can see that this dt are kind of canceling out like fractions, right? And we're left with ds and d time. Yeah? Yeah. So now all we need to do is just calculate these two things, multiply them, and we're done. So let's do that here. What is ds dt? Well, that is 10t. Taking the derivative of s with respect to big T, that's 5 times 2 times big T to the 1 power, yes? Yeah. What about dt d time? Well, that's just going to be 2, yes? Yeah. And the velocity of the particle, ds dt, is ds d temperature, which is 10t, times d temperature d time, which is just 2, so we'll call this 20t. Let's do another example. We talked about a balloon at the beginning, right? And so what is the formula for the volume of a balloon? We have the volume of a balloon, or any, we'll assume it's a spherical balloon, as a function of the radius of the sphere is equal to, anyone remember the formula for the volume of a sphere? 4/3 pi r cubed. R, the radius of the sphere, as a function of time, t, we will say is quadratic, 3t squared plus 1. So it starts out with some initial radius of 1, and then it depends quadratically as time goes on. And the question we want to know is, as you're blowing this thing up, right, because that's what this means. As time is going on, the radius is increasing quadratically. So what is the rate of change of the volume with respect to time? So we want to know what is dv dt. How we figure that out is we write, well, that's going to be dv dr times dr dt. See, because again, we kind of, in our minds, we're thinking about, the way that fractions cancel, numerators in the key fraction rule, leaving only the numerator of the first term and the denominator of the last term in the chain. But with these we can calculate, right? Because over here we can figure out, well, dv dr is just, what is that? That's 4/3 times 3, because it's r cubed. So I'll get rid of the 1/3, and we're left with 4 pi r squared. And then what about dr dt? Well, dr dt, since r is just quadratic, it's going to be equal to 6t. And now we can just substitute in right here. Yes? dv dr, 4 pi r squared, dr dt, 6t. Now, what if I wanted to get rid of the dependence on radius entirely in this? What would I do? Because here I've got my answer in terms of radius and time, but I just wanted time, right? Yeah. Do I have a way to get rid of this term r squared? Well, of course I do, right? Because I have an equation for r right here, right? This is then just equal to 4 pi r squared. Well, it's just 3t squared plus 1 squared times 6t. Let me do one last example just to show that this has broad application. I'll do an economics example. So let's say that the cost C of producing Q items depends on the efficiency E, which in turn depends on investment I. So by investing money into some manufacturing, you can increase the efficiency of the manufacturing, which will in turn reduce the cost. Kind of makes sense it would work that way, right? But we have to put some numbers on it. So the cost is going to depend upon the efficiency, so it'll be a function of efficiency. And let's say that that functional dependence is just $1,000 maybe minus 50 times E. So the larger the efficiency, you see we can reduce the cost, yes? And the efficiency is going to be dependent on the investment. And we'll say that dependence looks like a square root. We'll say it's just the square root of I. And I, of course, that's our independent variable. That's the thing that we control. We can invest more, invest less, and that will in turn affect the efficiency, which will in turn affect the cost. And so we want to know, rightly so, what the marginal change in the cost is for a change in investment. So dc di, if you will. And we can construct that with the chain rule, just as we have before. It'll be dc, I should make the c bigger because it's really a big C, right? Big C, de times de di, and we can calculate those from up here. So dc de is just going to be equal to minus, well, I need a minus sign. It's equal to minus 50, because e is just to the first power, and we're taking the derivative with respect to e. This term, of course, is 0, yes? And de di, well, this is to the 1/2 power, I to the 1/2 power. So the power rule still applies. It'll be 1/2 times I, oh, that's right, don't need the parentheses, it's just I. So what is 1/2 minus a half? 1/2 minus 1, I'm sorry, it's minus a half, right? So minus a half. So we can plug that in. That's going to give us minus 50 over 2, so we'll call that 25, over the square root of I. So there's your marginal cost, the change in the cost given a change in the investment. And I think that's it. That's the last application that I'll do. There'll be a few applications in the homework that you can do. I think you'll find it very straightforward. And I tell you, the chain rule you use a lot, especially in physics and engineering. It's very useful, saves a lot of time. It's totally intuitive once you get used to it, right? You have to work outside in. But that's it. There's not much more to it than that. Next time, I think we'll talk about implicit differentiation. We'll look at differentiating things like circles, for example, which would be difficult to differentiate with any of the techniques we've talked about so far, because, you know, a circle is... Put the axes down here and we think about that, right? You can see what the derivative is doing. Here it's pretty easy. You see the derivative is 0 at the top here. But on the sides, right, we have derivatives, basically vertical lines, right? That's a slope of infinity, right? Does the derivative exist there? Well, I mean, the only way we can really deal with this, with the differentiation that we've used so far, is by breaking this up into domains. We can deal with the top and then bottom, right? We have to kind of exclude these endpoints here. But we'll look at implicit differentiation, which allows us to find a derivative for things like the equation of a circle, much easier. So we'll talk about that next time. I'll see you then.